Welcome to this video on Ka, pKa and acid strength. We have introduced in the previous video the concept of the acid dissociation constant Ka. We're now going to look at its close relative, the pKa, and understand how that relates to acid strength. So what we've got in this table here is a bunch of molecules which are listed in order of increasing acid strength. So methane, you probably never really thought of it as an acid, but it's got a hydrogen in, so in principle it could be. Up through water, that's not really considered much of an acid either, but we've seen that that can behave as a weak acid. Then we've got your typical weak acids, things like ethanoic acid, methanoic acid, and then something like hydrochloric acid. And this is supposed to be the strongest acid that we currently know about, this carborane acid, which is predicted to have a Ka of 10 to the power 46. And if you think about, you look at these numbers, you can see that from water to that, there's a huge amount of variability. And that's quite inconvenient to have to deal with Kas of that magnitude. And so what we're going to do is introduce a new quantity, which is known as the pKa, in order to compress the variability. And the way we're going to calculate the pKa is using this formula. The pKa is the negative of the base 10 logarithm of the Ka. Now, what exactly does that mean? Well, the logarithm is a quantity which allows you to work out, so the reason for p here meaning power, the logarithm essentially tells you the power needed in the Ka. So let me explain that a bit better. This is a log base 10. It's like saying if I have a Ka, I want to know what power do I put here to get the Ka value. That quantity is the pKa, or minus the pKa. So the logarithm tells me what power do I put 10 to the minus in order to get Ka. So if you have a Ka that's going to be very, very big, then this is going to have to be a negative number, so you get 10 to a positive power. Whereas if you have a pKa which is, a Ka which is very, very small, then the pKa is going to be big. So these two formulae are really important that you learn. Ka, how you get pKa from Ka, and how you get Ka from pKa. So in terms of how you actually access a logarithm, there's just a very neat button on your calculator. So this would be the button that you'd use on a sort of class whiz style. This on an older style, log there automatically is log base 10. And you can tell because above it, if you do shift that button, you're going to get 10 to the power, which is what you need to turn the pKa back into the Ka. Over here, you've got the same. The only difference is here, it will give you logarithm to any base, and so you just have to make sure you type 10 to make sure you get base 10. So let's just show you how these calculations are going to work. You're going to just press that button. Let's say we try to turn this Ka into pKa. We're just going to do minus log base 10 of 1 times 10 to the 46, and we should get an answer of minus 46 if we do that. We can stick this number in the formula. Similarly, we're just going to have to do shift and then 10 to the power minus 7. So here that Ka would come out at 10 to the minus 7, which is 10 to the power 7. And times 10 to the 7. Leave this box blank for now, and just see if you can convert these Ka values into the pKa's and this pKa into the Ka. Well, here's what you should have got. So this is these are the numbers that you should have got in this case. So what we can see from looking at this table is that whereas Ka increases when we have an increasing strength of an acid, pKa actually goes the other way, and that's because of the minus sign. The minus sign in this pKa formula means that as you increase acid strength, you actually decrease pKa, and as you decrease acid strength, you actually increase pKa. Now I want to then show you what goes on for H3o Plus. This is a bit of a special case. We're thinking here about this species here, the hydronium ion, and what will its Ka and pKa be? And we'll just do that down here. So if we look at the Ka for H3o Plus, we can find its products over reactants. And remember, we leave out the H2O because that's got essentially a constant concentration. So we're going to get concentration of H3O Plus on the top from here, and then also a concentration of H3O Plus on the top. On the bottom, the denominator. Now these are actually then going to cancel each other out, and so we get a Ka value of 1. So acid in water has a Ka value of 1. If we work out the pKa, we're going to do minus log base 10 of 1. And that's just like saying, if I've got 10 to the power minus something, I want the answer to be 1. Well, the answer is 0. Anything to the power 0 comes out at 1. And therefore, the pKa of this is 0. So we put it in there. Now, why is that actually significant? Well, H3o Plus, we talked about in previous videos, is essentially what forms in water when an acid dissociates. And so if you have an acid which is actually better at dissociating than H3o Plus, what that acid's going to do when you put it into water is just form loads and loads of H3o Plus molecules. In fact, there's not going to be any HCl left. It's all going to have become H3o Plus. And therefore, these are the acids which we define as strong acids. So strong acids have pKa less than 0, or we could think about them as having a Ka greater than 1. And these guys are stronger than H3o plus. Now weak acids, in contrast, are going to have a pKa bigger than 0 and a Ka of less than 1. In contrast, so methanoic acid, ethanoic acid, chloric acid, water, they're all considered weak acid, well, these three at least. Now when it comes to water, water marks another kind of watershed, and the reason for that is because if you react a base with a particular molecule that you're trying to make it be an acid, then because these molecules are all stronger acids than water, they will be reacting with the base in preference to water. However, once you have an acid which is weaker than water, if you put a base into the solution, it just reacts with the water instead of with the acid. And so, weak acids really have to have, but must have, a pKa less than 14. So they're stronger than water. Anything else, so something like methane, it's just not really an acid. Now one final thing just to notice in terms of our original problem that we had with Ka's offering many orders of magnitude of variability. Look at the pKa numbers. They're increasing much slower. So here we've got an increase of an order of magnitude in Ka, or at least a decrease by an order of magnitude. 10 times smaller Ka results in just +1 unit in terms of the pKa. So pKa has compressed the variability and it's got an opposite trend in terms of acid strength.